So let's take a look at problem 2.9 from the practice exam. This is an example of a coplanar force problem or a two-dimensional problem. We're told that the resultant force acting on the support is to be 1,300 pounds directed horizontally to the right. We see that two forces act upon this support, one corresponding to the pull of the rope, kind of in the upwards and right direction, defined by this angle theta, and another corresponding to the pull of the rope, which we have denoted by this point B in kind of the right and downward direction. So what were we given? We know that the combination of those two forces, when they add vectorially, which by definition is the resultant force, should have an x component of 1,300 and a y component of 0. And the reason that we know that is we're told kind of in words that that resultant force should be directed horizontally to the right, meaning that the entire magnitude will be in the positive x direction. And we want to find the two parameters that define the force in the rope that I'll just call it A, even though A is likely a point here. And those two parameters are F and theta. So anytime we have a scenario in two dimensions where we have two unknowns, we're kind of tempted to approach the problem, if we don't want to think about it too much, by just decomposing both of the forces that are acting upon the support into x and y components and hoping that we can equate them on a component basis to the resultant force and be able to solve for these unknowns. We feel like that should be what should happen, that we have two unknowns. As long as we can write two equations, we'll be in good shape. So let's try that approach and let's see what happens. So I will begin by decomposing force F. So we're going to use the same approach as always. We'll decompose F into an x component and a y component. So we can view it as the side length of this force triangle corresponds to the magnitude of force F, which we don't know. The geometry is defined by that angle theta, which we don't know. However, we know that we can decompose this into x and y components by just using simple trigonometry. If you're watching this video first, just in case, remember this is all based on SOHCAHTOA. For example, if I look at the definition of the cosine of this angle, ka, it will be the ratio of the adjacent side length, which is f sub x, divided by the hypotenuse, which is f. I can solve that for the component I want, which is the x component, and find that it's just the magnitude times the cosine of theta. Sorry, it's a nice day out, and there's lots of people walking around outside. That's what keeps drawing my eye over that way. In a similar fashion, if I look at sine theta, defined as the ratio of fy over f, I can express fy as just f sine theta. So that's not a very meaningful approach because these are both the two unknowns that I don't know. But again, I'm going to try to kind of match these up on a per component basis and see if I can solve for them. So that's kind of the decomposition of F. For the decomposition of the 900-pound force, which we'll call F900, the only thing that's a little bit tricky about this is we're not given a geometrical description that's typical, which would allow us to kind of just use our traditional to get the x component multiplied by the cosine, to get the y component multiplied by the sine. Remember, you can only do that if the angle that you're provided is referenced from the positive x-axis and measured in the counterclockwise direction. In the case where you have an angle like the 60-degree angle, if you want to work directly with what you're given, you have to do a little bit of the work. So we know that the resultant, which lies along the hypotenuse, has a magnitude of 900 pounds. What I'm interested in doing is decomposing this and then x and y component. So we notice that in this case, the x component will be opposite the 60-degree angle. So even though you might be familiar with multiplying by the cosine of whatever angle you're given in order to get the x component, in this case, it is actually the sine, because notice in our right triangle here, again, that x component is opposite. In a similar fashion, the y component will not only be adjacent, so I will have to use cosine, but notice in this decomposition that it will point in the negative y direction. So this is going to be minus 900 times cos 60. So that's what we know in terms of the decomposition. Thus, we know that the resultant force is going to be the vector sum of force F plus F sub 900, and this yields two scalar equations. This tells me that the x component of the resultant force must equal the x component of F plus the x component of the 900 force, which means that 1,300, again, I'm going to go up here and get the x component of the resultant force, is equal to the x component of f, which is f cos theta, and plus the x component of the 900 pound force, which is plus 900 sine 60. So getting a little bit squished there in my writing. I'll move over more to the left for this time. So the resultant component of y, the y component of the resultant, I should say, is equal to the y component of f plus the y component of the 900. Now notice that the y component of the resultant force is 0, and that will be equal to the y component of f, which is f sine theta, plus the y component of the 900 pound force, which is minus 900 cos 60. So these equations look a little bit different because they can't be written as a linear combination of two independent variables. It's not something times x plus something times y equals a constant. So I'm going to go and take these and kind of move them over to the right and rewrite them. And here is actually how I will write them. I will isolate my unknowns because usually that's kind of a good approach if you don't know mathematically how to manipulate them. So this is from the x equation. What I will be able to find is that f cos theta equals 1300 minus 900 sine 60. So I know this is just a number. I would have to compute it, but it is just a number. And from the y components, I can manipulate this and write that f sine theta equals 900 cos 60. So you might wonder, how am I ever going about making these two equations into a single equation with a single unknown? And if I label this 2 and I label this 1, remember that when you solve system of equations through like elimination, if you follow Gauss's rules that you might have covered in a basic linear algebra class, you can write the ratio of the two equations, and the solution to that ratio will still be a valid solution to the original system. So if I do that, I will get f sine theta divided by f cos theta. So you see the advantage there is I can cancel my unknown f term and reduce this to a single equation with a single unknown. And that will be equal to, in the numerator, I'll have the y equation term, which is 900 cos 60, which looks intimidating, but again, it's still a number. And in the denominator, I will have 1300 minus 900 sine 60. So let's actually, and of course, sine theta divided by cosine theta is equal to tangent theta. So let's actually put this in our calculator. So let me actually write above that this is equal to tan theta. So what I need to do is, let me take and compute that ratio first. So in the numerator, I have 900 times cos d of 6d. So if you're using a calculator, make sure that you're in degree mode. We do it in MATLAB by use kind of appending a d onto the end of the function. And in the denominator, we have 1300 minus 900 times sine 60. I got it all in there. That's good. So what I want to do now, going back to my .cam, 0.8644, that is the tangent of theta. So tan of theta is equal to 0.8644. So what I need to do to find theta is take the arctangent or the inverse tangent of that quantity. And what I will get is, so I can just say a tan d of the answer. That will give me to 3 sig figs 40.8 degrees. So that would be 40.8 degrees. So I have one of my two unknowns. Now all that I need to do, just like any solution to a system of equations, is to substitute that back in to one of my two equations. So I will substitute back in here, since this is probably the easier equation to work with. And what I can find is f is going to be equal to 900 cos 60 divided by the sine of theta, which I now know to be 40.8 degrees. And if I compute that, that will give me 900 times cos d 60, and then I will divide that by sine d of, I'll keep the entire precision of the answer in there. And I'm getting 688 pounds rounded to 3 sig figs. So hopefully that was helpful. It might have looked like a relatively easy problem on the surface, and it definitely wasn't too bad. But all of the complexity there comes from how you solve that system of equations due to the way that the two unknowns are coupled as a product rather than being independent terms which are added together, which lets you use all of your traditional linear algebra techniques. So when you have that kind of environment, the usual trick is to divide one equation by another and try to isolate the unknown angle in terms of a tangent function.